It seems like every time there's a discussion of metabolic acidosis and the anion gap, people's eyes glaze over. This concept tends to strike fear in the hearts of med students and maybe even some interns and early residents. And it seems like the conversation inevitably turns to the mnemonic mud piles, and that's where we end up without really getting anywhere diagnostically. So we're not going to beat the mud piles horse to death in this lesson. We're going to make the material a little more intuitive, easier to understand, so that the information will actually be diagnostically useful without having to go back and relearn how to calculate the anion gap or what exactly it means. Now, this material is geared more towards medical students and residents, and you should have a good understanding of the bicarbonate buffer system and renal physiology in order to understand the material. So remember that we can represent any acid generically with the symbol HA. This acid is going to deprotonate, shed its proton, and the molecule left behind after deprotonation is going to be what's called the conjugate base. Now remember, the proton here is a cation, and the conjugate base is the anion. And for medical purposes, typically the acids we're dealing with end in IC, such as salicylic acid, and the conjugate base will be an 8 anion, such as salicylate. And here's important concept number 1. An acid will leave behind a footprint to let you know that it was there. And this footprint is the conjugate base, which is an anion. Now let's take a look at the serum chemistry panel. Now here we're going to have cations and anions measured. Primarily, the cation of the body is going to be sodium. And even though potassium also constitutes a cation, its concentration is mainly intracellular. It's not going to have a very high serum concentration. So for simplicity, we typically ignore this. On the anion side, we measure bicarbonate and chloride. Now, these two columns need to add up to each other because the net charge in the body is 0. But they don't, because we haven't counted all the anions. There are some significant anions in the serum that we just don't bother measuring, because typically we don't need to. So what we're left with in the anion bar graph is a space. And what we're saying is, we know that the unmeasured anions are in this space, we just don't care about them. So basically, it's like we started sorting our laundry, and we made a basket for bicarbonate, a basket for chloride, and then we just left a basket for everything else. And in that basket, we threw in things like sulfates, hippurates, and albumin, which is also an anion. That's right, I said albumin. Now, don't let this confuse you. I know we measure albumin in the LFTs. However, that's a mass measurement. It's measuring grams per deciliter. 1 molecule of albumin is a big molecule, but it only contains 1 unit of negative charge as an anion. So for charge purposes, what we're really concerned with is the quantity of albumin, not the mass. And quantity is going to be measured in millimoles per liter. And according to data published in 2006 by Din et al., 1 gram per deciliter of albumin only equates to 0.12 millimoles per liter. That means even if someone has the normal 4 grams per deciliter of albumin, that still only results in a net quantity of 0.48 millimoles per liter, which is less than half a point. And that's why we don't care. And that's why we toss it in the everything else laundry basket. So this everything else laundry basket, once we total it up, it comes out to about 8 to 16 millimoles per liter of unmeasured anions that we really don't care to measure. But we do have to label this basket something. So what we labeled it was the anion gap. Now, typically, we're not directly measuring it. As I said, it's a bunch of unmeasured anions. And normally, we don't care when there's not an acid-base disturbance. But when your patient is in a metabolic acidosis, you're going to have to know how big that basket is, because things can be hiding in there that you didn't expect. And that's why we calculate the anion gap, because it's a hiding place. Basically, what we're doing when we calculate the anion gap is we're measuring the size of that basket and how much stuff is in it. And if we find out that there's too much stuff in that basket, then someone's been tossing their laundry into ours. And that someone will typically be whatever acid is causing the acidosis, because the extra laundry is more unmeasured anions, which are probably the conjugate base from that acid. And now it's time to actually calculate the anion gap. Now, this is a simple calculation. It shouldn't incite fear, and there's no excuse for not remembering it. It's simple arithmetic. It's not a complicated formula. And that is cations minus anions. Now, the only cation we care about is sodium, and you subtract the 2 anions that we measure, which is bicarbonate and chloride, and whatever's left is the anion gap. But don't freak out if when you calculate this manually and you look at your lab results, the anion gap that's in the lab results doesn't match. What's going on is simply that some labs take potassium into account as a cation, and they include that in the calculation. So their calculation ends up being sodium plus potassium minus bicarbonate minus chloride. Whether or not to include potassium really is a matter of preference. I typically don't, but I haven't really found any literature which supports one method over the other. So if you include potassium, your normal range should be about 12 to 20 millimoles per liter, because serum potassium runs about 4. An easier way to remember this is without potassium, the range is 12 plus or minus 4, and with potassium, the range is 16 plus or minus 4. Now that we know what the anion gap is and how to calculate it, we can use it to start whittling down the differential diagnosis for the patient in a metabolic acidosis. So in human physiology, we deal with the bicarbonate buffer system, and essentially one of two disturbances is occurring. The first thing that can occur is that additional acid is being added to the system. And adding acid to the system is going to leave behind a conjugate base, and therefore is going to increase the anion gap. So what we can say is that processes that increase the acid present in the system are going to result in what's known as a high anion gap metabolic acidosis. But hold on, it's not time for mud piles yet, because mud piles is nothing more than a list of a bunch of etiologies. But those etiologies really boil down to just 5 mechanisms. And I do have to take a moment to give recognition to one of my mentors, Dr. Michael Stanley at the Kauai Delta Emergency Medicine Residency, for really simplifying this for me. So here they are, the 5 mechanisms of a high anion gap metabolic acidosis. And the mnemonic that Dr. Stanley uses is KLUES, K-L-U-E-S. So really it comes down to either ketone production, lactic acidosis, uremia, quote, ethanols, which is going to help us remember toxic alcohols, and salicylate poisoning. So ketones are the byproducts of fatty acid metabolism, and these are beta-hydroxybutyric acid and acetoacetic acid. These are both ionizable acids. They'll shed a proton, causing acidosis, and the resultant anions are going to be beta-hydroxybutyrate and acetoacetate, and this is what's going to increase the anion gap. Lactic acidoses are a special group, and we'll cover these in another video, because many things will result in a lactic acidosis, so I'm not even going to begin to cover those. Suffice it to say that any process that interferes with oxidative phosphorylation or any process that causes tissue hypoxia is going to result in lactic acidosis. But the interesting thing about a lactic acidosis is that lactic acid is not being produced, and that is not the source of the protons that's causing the acidosis. Lactate is being generated directly, and the protons are actually coming from a different source. It's kind of a kooky one, and I'll cover this in another video. But fortunately for us, the end result is the same. You get an acidosis, and you get an increase in an unmeasured anion, which is lactate, and we can always just send a serum lactate to figure this one out. U stands for uremia, which indicates renal insufficiency or renal failure. Now, the interesting part here is that you don't get a true high anion gap metabolic acidosis. There's also a concomitant non-anion gap metabolic acidosis associated with this. So the elevated anion gap results from the decreased elimination of anions that we're typically able to clear, such as sulfates, urates, and phosphates, which is going to elevate the anion gap. And the acidosis results from the inability to excrete acid and acidify the urine. This is what causes the high anion gap portion. However, the decreased reabsorption of bicarbonate is also going to result in a non-anion gap acidosis, but we'll cover this a little later. Next on our list, we have, quote, ethanols. Now I say quote because one of these compounds is not an ethanol. It's not a 2-carbon compound. The 2 compounds to worry about here are methanol, which is basically moonshine, and that's going to be metabolized to formic acid, and ethylene glycol, which is antifreeze, and that's going to be metabolized to oxalic acid. And these are going to produce the anions formate and oxalate, respectively. Now, I did not mention isopropyl alcohol because that does not cause an acidosis and will not elevate the anion gap. The end product of metabolizing isopropyl alcohol is actually acetone, which neither causes an acidosis nor is it an anion. And I'll cover that a little more when we talk about toxic alcohols. Finally, we have salicylate poisoning. So basically, salicylic acid, such as aspirin, is going to be deprotonated, resulting in the anion salicylate, and that can also be measured in a serum assay. Okay, so now it's time to talk about mud piles. So mud piles is just a mnemonic for a bunch of etiologies that will ultimately result in one of these 5 processes. So what we can basically say is that mud piles etiologies cause clues type acidoses, and all of those are high anion gap metabolic acidoses. I'm not going to go over mud piles specifically. You guys can look that up on your own. But it's starting to look like mud piles is a little bit outdated. There are some newer mnemonics out there. For example, the Goldmark mnemonic that was proposed by Brubaker et al. And you can take a look at that one at StatPearls on the PubMed website. Now it's time to switch gears and start talking about non-anion gap metabolic acidoses. An analogy that I've used quite a bit when talking about gap versus non-gap acidoses is that of a crime, specifically a murder versus an abduction. So in a murder, you have a body, you have something there to examine, and typically that's a high gap acidosis where you have an elevated anion gap, and whatever ingredient is elevating that anion gap, that's going to be the source of your acidosis. But I tend to think of non-gap acidoses like an abduction. It's not something that was done and there to be examined. This is more something was taken away. So non-gap acidoses are the result of a loss of buffering capability. In other words, they result from a loss of bicarbonate. Now, because we're not adding any acid to the system, then there's not going to be an increase in unmeasured anions. So the anion gap will remain normal. But what will occur is a shift in the measured anions. So let's draw our ion bar graphs once more. And by the way, these are known as ionograms. In the cases that we just discussed where there's a high anion gap metabolic acidosis, the process that is creating the acidosis, the acid-producing process, is expending bicarbonate, because one molecule of bicarbonate has to be expended for every new proton in order to buffer that and keep the pH steady. And the trade-off was that there was an increase in unmeasured anions from whatever the acid-producing process produced. Now, in the case of a non-gap acidosis, there is no increase in unmeasured anions because there is no increase in the acid-producing process. The problem here is a primary pathological loss of bicarbonate. And so the bicarbonate wasn't lost in buffering, it was primarily wasted. And thus the unmeasured anions stay the same, so the gap doesn't change. But there is a loss of bicarbonate, and there has to be some sort of shift in order to compensate for that. And what shifts is chloride, and that is our other measured anion. So basically bicarbonate is going to be traded for serum chloride, and this works in two phases. First, the loss of extracellular negative charges from the loss of bicarbonate is going to pull chloride extracellularly to compensate. And so there will be a hyperchloremia. And then over the course of the next couple of days, if this acidosis continues, the kidneys will respond by reabsorbing more chloride in order to balance out the loss of negative charges. And this will continue the hyperchloremic state. And now we've shown why non-gap acidoses are sometimes referred to as hyperchloremic acidoses. Now, the mechanisms by which bicarbonate is lost essentially come down to two processes, either GI losses or renal losses. The most common source of this is diarrhea, so an increased transit time reduces the reabsorption of bicarbonate in the gastrointestinal tract, and you basically waste bicarbonate in the stool. Another way that this can happen, this kind of a zebra, is a pancreatic fistula, where you have basically dumping of bicarbonate from the pancreas into the GI tract. Renal losses will occur for a couple of different reasons. Number one, we've already talked about, is renal failure. And so the inability to reabsorb bicarbonate from the proximal convoluted tubule will result in bicarbonate wasting. And remember that new bicarbonate is also generated in the proximal convoluted tubule, so this process is going to be affected as well. Another pathologic source of renal bicarbonate wasting are the renal tubular acidoses, so these are worth also looking up. And finally, iatrogenic losses are also possible. So one of these is acetazolamide or diamox administration. If you remember, this is a carbonic anhydrase inhibitor, which basically inhibits bicarbonate reabsorption in the proximal convoluted tubule, and therefore you'll have bicarbonate wasting. Another mechanism that can happen is actually normal saline administration. So like we talked about before, chloride and bicarbonate are linked to each other. When one changes, the other one shifts. And so therefore, if someone receives a large normal saline bolus, they're receiving a large chloride load in the serum. That's going to cause some shifting of serum bicarbonate intracellularly, and that's going to result in an acidosis. And this has been shown in a few different articles. There is a good mnemonic for remembering some of these non-gap acidoses, and that is hard up. And one site I've seen mention this one is Life in the Fast Lane, and I'll have their link in the description for you. All right, so now let's recap by comparing and contrasting high gap versus normal gap metabolic acidosis. So in a high gap, the primary disturbance is going to be increased acid production. Now, side note, this could also be a decreased acid elimination on the part of the kidneys, but the overall process is still going to be the same. There's going to be a net increase in acid of the system. In a non-gap, the main problem is a loss of buffering capability via bicarbonate wasting. The unmeasured anions in a high gap are going to be elevated because these are either going to be the conjugate base to the acid that's causing the acidosis, or the acid-producing process is going to produce anions in and of itself. The non-gap acidosis is going to have no change in the unmeasured anions because there is no increase in net acid. Chloride, which is a measured anion, does not change in a high gap acidosis, and that's because the loss of bicarbonate is creating a space that's essentially being filled by the increased unmeasured anions. In a non-gap acidosis, there is no increase in unmeasured anions, and therefore the space left by the loss of bicarbonate will actually be filled by chloride shifts. The mechanisms that produce a high gap acidosis will basically be the Clues processes that we talked about earlier, whereas in a non-gap acidosis, the mechanisms are either GI or renal mediated. And to remember the etiologies that cause high anion gap metabolic acidoses, you can use the mud piles or the gold mark mnemonics. And for the non-gap acidoses, you can use the hard up mnemonic. I hope this lesson helped to clear up some of the mysteries behind the anion gap and its role in metabolic acidoses. We hope to be rolling out more new content here soon. If you haven't already done so, please subscribe. And as always, remember, don't aim to memorize, aim to understand so that you can apply what you've learned.